All right, well, happy Friday. It is the end of our second week. So we are, I guess, 1/5 of the way through the quarter. And yeah, and today we'll take a look at environments and scoping rules. And so this is, this lecture covers a lot of kind of nitty gritty details on how R works. And a lot of it you actually don't have to worry about if you have good kind of coding practice, right? So if you follow these good things about writing code, you know, that your functions inside your function, all of the values are defined inside the function, and it's not asking for values that don't exist inside the function, we don't actually have to worry a lot about these environment and scoping rules. But R has kind of this design philosophy that says, you know what, if you give me a function and you give me some code to run, R is going to do its best to run it. And sometimes that means you give it a function where all the variables are not defined inside the function. And so R is going to do its best to try to search for these values. And so the way it searches for the values is through these scoping rules. Okay, versus some other languages, you know, if you give it a value inside, if you ask for a value that's not defined inside the function, the language just fails. It just gives an error and says you're not allowed to do that. Okay, and so anyway, to kind of explain this, and there might be situations where you have to read someone else's code, or you know, you come back and you read your own code that wasn't well written, or something. You might it's useful to learn how environments and scoping rules work. Okay, and so, you know, at the heart, we have to just kind of talk about how, you know, values and environments and things like that work, right? Okay, so I think there's a few concepts that we're already familiar with, and that is, you know, when you work inside R, you have you know, you're kind of working in your global environment, okay? And that's kind of your workspace. Okay. When you execute a function, the function creates its own local environment, okay? And objects that are created inside the function are accessible only within the function, and they don't appear inside the global environment, okay? And anything that's in kind of the local environment will take precedence over objects that exist in the global environment. And if you have kind of two objects with the same name, the local one, the one kind of in its immediate scope, will mask the other object with the same name, right? And so, right, and so, okay. And what we want to do is we want to formalize these ideas and give, you know, just kind of a little bit more specific ideas for how this stuff goes. Okay, so at the beginning, let's just talk about naming objects. Okay, so here I create this object. It's this vector, values 1, 2, and 3, and I assign it to X. Okay, and what we're doing is we are actually taking the name X and we are binding it to this object 1, 2, 3. Okay, and so this creates an object with the values 1, 2, 3 somewhere in memory. Okay, there's like a location in memory with an address, and we are binding the name X to that location in memory. And so anytime we call the name X in R, what R is going to do is it's going to go to that location in memory and it's going to find it. Okay, now I don't know if you've ever taken some kind of CS class or something where you ever try to write things in assembly, but like in assembly language, just you write things directly with kind of the memory registers, and you just, you know, you put values inside this location in memory and you alter the values inside and at that memory address and things like that. And you know, it's a lot harder to write things that way, whereas, you know, a language like R, you can just kind of do things on the fly, and R handles a lot of stuff in the background for you.
Could I ask a question?
Yeah.
So sometimes when creating objects in R, I just use the equal sign. Is that doing the
That's
same
the same.
thing?
Yeah.
Okay, cool.
Yeah.
Okay, thanks.
That's fine. Again, you know, the traditional operator is this arrow thing, but you know, almost every other language uses equals, and so R kind of allows for that. Okay, it is kind of like the comparison is like you're speaking with a different accent, and you know, it's like if you were from the UK and you came to the United States and you spell the words color with a U in it, you know, that will kind of give you away as a foreigner or, you know, someone from England or something like that. Okay. And,
Okay, got it.
and
Thank you.
that's kind of what it's like. People will understand, and
Okay.
and the program will work. But you know, when someone else reads it, they're like, oh yeah, you're not from around here. Okay, so what we're doing here in these lines of code, okay, I create this object 1, 2, 3, and I give it the name X. Okay, and then I say X and I assign it to Y. And basically what I'm doing is, you know, I have this, I first create this object and I point the name X to this object. And then I point the name Y to the same object. Okay. And then I, in this line of code, I create another object that also happens to be 1, 2, 3. Okay. So I guess I can write. Okay, so I've got, you can't even read this. Okay, so I got 1, 2, 3 here, and then I've got, so here I've got 1, 2, 3 up here, and I've got X and Y both pointing to it. And then on the other line of code, I create another thing with 1, 2, 3, and Z is pointing to this, okay? So they are two separate things that both happen to have the values 1, 2, 3, but I've got X and Y associated with this object, and Z is associated with this, okay? They are distinct objects though. So, so these are, the variables are references to memory locations. So X and Y actually point to the same one, whereas Z points to a different copy or a different object that has 1, 2, 3, okay? And kind of the memory allocation issues, they're all handled by R automatically. It's got a garbage collector and things like that. You don't have to worry about these things, okay? Now, when you modify something, okay? When you modify something in R, what it does is it creates a copy. We have this system called copy on modify. Okay, so I've got 1, 2, 3. X has the value 1, 2, 3 here. And then I'm going to take X and Y are both pointing to this. But then when I say change the third item in Y to 4, R is going to say, oh, you know what? I need to create a new thing. Okay. Okay. And so when you call 1, 2, 4, or say change the third item to 4, it's going to suddenly, it starts off like this, 1, 2, 3, and then you say change it, and then it creates a copy. And so this is still X is still 1, 2, 3, and now this thing down here is going to be Y. Okay, that's different from other languages. So for example, if you have Python, and you did something like this, the X would also change to 1, 2, 4. Okay, so there's different kinds of things. R, when you modify something like this, it's going to create a copy, and it's going to copy it and modify the copy. So assignment binds a name to a value, and scoping is the act of finding the value associated with a name, right? Okay, and the scope of a variable is kind of the region where this name or the where the variable is defined. Okay, and so so here I think the basic rules are simple, right? So here I'm going to assign 1 to Y in the global environment, and inside and I create a function called G, right? And this is, again, this is and inside of G is a function of X, okay? And so we take in an argument X, and inside of G, we're going to say Y is going to get the value 2, and we say G is going to return X plus Y, right? So what is G of 3 going to return? G of 3 is going to return the value, what do you guys think? 5, okay? Simple, right? So we call G of 3, X takes on the value 3, so this is the value 3, and then it says X plus Y, and inside of G, Y takes on the value 2, so it's going to return X plus Y, which is 3 plus 2, it's going to return 5. It doesn't care about this Y out here, okay? And so indeed, G of 3 returns 5. Okay. Now, this is where R's lexical scoping rules come into play, okay? Here I have a function f, okay? And this is a poorly written function. And, and so this is poor technique to reference objects that are not defined inside the function. But rather than return an error, the design philosophy of R is just, you know what? Just do your best to run the code, okay? So inside of f, it's a function of x, okay? And we have no reference to y anywhere, okay? We don't ask for a y, we don't do this, but it's going to say x plus y. And so, you know, if we call f of 3, it says, all right, well, what's 3? X is 3, and then it says, well, what's y? And it can't find y inside of f. And so R, rather than return an error, R is going to say, all right, let's go looking for y, okay? So it's not inside of f, and so it goes to the global environment, says, oh, look, I found y, and y gets the value 1. And so f of 3 is going to return 4, okay? And again, a lot of the issues that I'm going to be talking about today is a non-issue if you only write functions like this, where x comes in with the argument, and if you ask for y, it's defined somewhere inside the function, okay? So if you only write functions like this, you don't have to worry about scoping rules, okay? But there are times where, you know, you might encounter a function like this, where it's asking for a value that doesn't exist inside of here, all right? And so how does R handle this? It uses scoping rules, okay? And that's what today's lecture is all about. Okay, so let me just read this kind of wall of text here. Okay, variables defined within a scope only exist in that scope and only for the duration of that scope. If variables exist with the same name outside the scope, those variables are separate and they don't interact with the variables inside the scope, nor are they overwritten or changed. Okay, a function is its own separate environment and it only communicates to the outside world via the arguments going in and the returned object going out. For example, inside the function, if you execute the command rm list equals ls, which is what we use to delete everything in the environment, okay, and that's a terrible idea, but if you did that, it would only delete the objects that have been defined inside the function, okay? It wouldn't touch anything in the global environment. The exception is there is something called super assignment, and we'll talk about that at the kind of the last few slides of the lecture. Cover super assignment, and that searches a higher scope on the global environment. But in general, this is a dangerous operator and it should not be used, okay? So I recommend against super assignment. Sometimes you'll read other people's code and the super assignment operator is being used, and you know, I suggest stay away. All right, so here we're going to define x, y, and z to get the values 1 inside the global environment. And inside the global environment, I define the function f. Inside the function f, y gets the value 2. Inside f, I define another function g. And inside of g, z gets the value 3. What g will do is it returns the value x plus y plus z. And what f returns is it returns the value of g running. Okay, so if I run f, what will it return? Okay, so when we execute f, we come here and we say, all right, here's f. Inside f, y gets the value 2. And then let's just kind of skip this. And it just says return g. Okay, well, we say, well, what is g? Okay, well, g is this function. Inside g, z gets the value 3, and g is going to return x plus y plus z. All right, so we say, well, what is x? X doesn't exist here. And we search the higher scope, it doesn't exist here. And so we end up in the global environment and we take the value 1 for x. Then we want to add y. Well, what is y? Y doesn't exist inside of G. So we search the higher scope and we take the value 2. So we have 1 plus 2. And then we're going to add Z. And we find Z right here. Z takes on the value 3. So we're going to do 1 plus 2 plus 3. And G is going to return 3. G returns, returns 6. And so F is going to return 6. Okay. So when we run this, F will return 6. After running F, what will be the values of X, Y, and Z in the global environment? Those are all unaffected, and they're all going to remain 1, 1, 1. Okay, so F returns 6, and X, Y, and Z in the global environment are all 1, 1, and 1. All right, so far so good? Okay. Have I given you any letters today? Not yet. Okay. Okay, first quiz answer is B. B as in bear. B as in bear is the first quiz answer. Okay, so let's talk environments in kind of formality here. The environment is the data structure that powers scoping, okay? The job of an environment is to associate or bind names to values. And you can think of an environment as a bag of names, okay? And each of those names point to an object stored in memory. So here you can actually create your own new environment, okay? And inside the new environment, we're going to say, we're going to take the name A and bind the value false, bind it to the value false. We'll take the character string A and bind it to the name B. We'll take the value 2.3 and bind it to the value C. And we're going to take the vector 1, 2, 3 and bind it to the value D. Okay, and so this is kind of our picture here. Okay, so A is false and B gets this and C gets that and D gets this vector here. Okay, and environments themselves are objects, and you can work with the environment kind of like you work with a list, okay? And that you've got double bracket and $ operators. You ask what's the type of for the E, and it's an environment. You can ask, okay, well, what is the value of C inside the environment? And it says, yeah, that's 2.3. What's the value of D inside the environment? And it says, oh, that's the vector 1, 2, 3. Okay, but environments are unordered. Okay, you kind of think of it as a bag or a purse or something. And if you say, well, what's the first object or what's the fourth object in the bag? There's no ordering. So R says you can't ask me for what the first or fourth or fifth object is. These are kind of the wrong arguments to be using for subsetting an environment. So you can't a numeric index will produce an error. You have to reference everything by name. Okay, you can list off all of the objects that exist inside an environment with ls, okay? And so that gives you kind of the vector of character names of the environment. And you can also ask for some more details with structure, and this will kind of give you all of the details for the objects inside the environment. Okay, and again, unlike lists, so you kind of interact with environments similar to lists, but they're a little bit different. Okay, single square brackets do not work, okay, in that you can't, get like multiple values back, okay? And if you assign the null object to something, to a name, it doesn't remove that, okay? So kind of normally in a list, if you assign null to an element in the list, it just kind of kills, it removes that element from the list. Whereas here, if I do this, D is going to be a name associated with the null object, okay? And so if you want to actually remove an object from the environment, you use the rm function, okay? And normally you just call rm without the environment argument here, and then it works in the global environment. It just kind of removes objects from the global environment. But here you can kind of specifically say I'm working with environment E or something. All environments have a parent environment, okay, which is another environment, okay, and so you have in these diagrams, this environment has a parent environment here, and this environment has the parent environment here, okay? And so the parent environment is what powers lexical scoping, okay? If an object, if a name is not found inside the current environment, R is going to look in its parent. And if it doesn't find it there, it's going to search that parent and keep going all the way to the end. And there's and all environments have an environment, have a parent except for the empty environment. So the empty environment is kind of like the, I don't know, the grand ancestor of all other environments. And that's the only one that has no parent, okay? But every other environment has a parent, and R kind of climbs that hierarchy when searching for names. Okay, there are kind of 4 special environments that we should mention explicitly. All right, the global environment, your workspace, that's where you work. And the parent of the global environment, this is a little bit strange, but the parent of the global environment is the last package that you attach. So when you call library ggplot2, that's going to become the parent of the global environment. If you call library dplyr, that's going to become the parent of the global environment. Any library or package you attach, that's going to become the parent of the global environment. Okay. The base environment is kind of the second to last environment in the hierarchy, and it's the environment of the base package. Okay, base is where kind of your functions, your regular old functions like C to combine values, or matrix to create a matrix, and things like that. Those exist inside the base package. Okay, and that has the parent of the empty environment. Okay, so the parent of the base environment is the empty environment. The empty environment basically has nothing in it, and it's the only environment that has no parent. Okay, it's the only environment that has no parent. Okay, and then if you call environment, that's going to be your current environment. Okay, so the search path, when you call for search, it lists all of the parents of the global environment. All right, and this is the search path because objects in the environment can be found from kind of the top level interactive workspace. So you know, if I create a vector, okay, x is 1 through 5, okay, and if I say I want to take the standard deviation of x, it calculates the standard deviation of x. But the standard deviation is not defined in the global environment. I never wrote a function called standard deviation, yet R is able to calculate the standard deviation, okay? And the reason for that is you can say, okay, well, what is the standard deviation if you, oh, you know what? Let me restart R. I forgot I loaded some stuff here. Okay. I can take the standard deviation of x, and if I ask for details on the standard deviation, it says namespace stats. Okay, so the standard deviation is a function that exists inside the environment stats. Okay, and stats is one of the libraries or one of the packages that get loaded when you start up R. When you start up R, it loads up kind of these packages: the base environment, methods, data sets, utils, things like that, graphics, stats, also RStudio and things like that. So package stats, standard deviation exists in here. And so even though I never defined a function standard deviation inside the global environment, it actually, package stats, standard deviation actually exists as a function inside this thing. Okay, so normally you just look at the global environment, but you can actually check out like what functions exist inside base and things like that. Okay, but anyway, that's what we have here. Okay, when you ask for things like what's the mean of x, okay, you get the, and again, I never defined the mean, but the mean exists inside the base. Okay, and so what R does is when you ask for the function standard deviation, it says, well, I don't see it in the global environment. So it searches all of these other things and it finds it in package stats here. Okay, so this is kind of the diagram showing how these libraries or environments are linked. you start off in the global environment. All of these packages, okay, are in there. Okay, one of them being stats and one being data sets and things like that. Okay, and then base exists here, and then we have the empty environment. Okay, so when you ask for things like letters, okay, we can ask for environment of letters. Okay, did that not work? Well, maybe I'm making stuff up here. Okay, but so anyway, so we have the base environment and our empty environment. I don't know. Do you have things like empty cars? That's a thing, and I think maybe wait. How do I find out the environment of? I think I'm doing this wrong as far as finding out where the environment is. Okay. But anyway, when you load a library, it loads it into the search path, right? So if I currently have packages A, B, C, right now the parent of the global environment is package C. If I load a new library like package D, that's going to join, and that's going to become the new parent of the global environment. Okay, and the parent of package D will be package C. The parent of package C will still be package B, and so on and so forth, until you get to the base environment, whose parent is the empty environment. When we call functions, okay, environments are created as a result of kind of calling functions and stuff. And functions have an enclosing environment, a binding environment, an execution environment, and a calling environment. The enclosing environment is the environment where the function is created. And every function has one and only one enclosing environment. Okay. As far as the other types of environments go, there could be 0, 1, or multiple. So a binding environment is where the name of the function resides. Okay. So binding a function to a name with the assignment operator defines a binding environment. That's where the name is located. When you call the function, right, and you execute it, that creates a temporary execution environment, and that's where all kind of the variables inside the environment inside the function exist. Okay, and any time a function is called, the execution environment has a calling environment. That's the environment from where the function was called. Okay, we have a question. It says, do packages C, B, and A have equal relation, or is B the parent of C and A is the parent of A? So here, A is the parent of B is the parent of C is the parent of D, and D is the parent of the global environment. Here, A is the parent of B is the parent of C, and C is the parent of the global environment. Is that okay as far as these diagrams go? I hope that answers your question. All right, so most of the time, if you create a function inside the global environment, then the function, then the enclosing environment is the global environment. That's where the function is created. And the function is named inside the global environment. And so the binding environment is also the global environment, okay? And a lot of times, the environment where the name exists and where it was created is going to be the same, okay? So in most scenarios, the enclosing environment and the binding environment is the same. We run into a distinction between the enclosing environment and the binding environment when we are talking about packages and things like that. Okay. So here's a simple example. I've got y gets the value 1 in the global environment. And inside the global environment, I create a function f, okay? And the function f was created in the global environment, okay? So the environment of f is the global environment. And the name f exists inside the global environment. And so, so it's also the binding environment. Now, you know what? This stuff doesn't work because the environment thing only works for functions. That's what's going on. Okay, so so f the enclosing environment is the global environment, and the binding environment is the global environment in this scenario here. But you have other things like these packages, and things are a little bit stranger, okay? So if you look at the definition of the standard deviation function, okay, the definition of the standard deviation function is that it is the square root of the variance, okay? It calls for the function variance and, you know, some other stuff, but basically it asks what's the variance of x, and then it takes the square root of that, okay? The standard deviation's namespace is stats, okay? And so here's the thing. If you load up your packages, the parent, in a different order, the parent environment will kind of change, right? So if you load package A, then B, then C, then the parent of B will be A. But if you load packages C, then B, then A, then the parent of B will be package C, and things like that, right? So does this mean that if it's searching for a function, is it going to find different functions if the packages are loaded in different orders, right? And that would create a problem. So the standard deviation function being defined in terms of the function variance var, okay, how can we make sure that whenever we call the standard deviation, that it's going to always use the correct variance function, not something else, okay, that's affected by the search path. So R handles this by using kind of namespaces, right? And so to kind of ensure that packages work the same way, regardless of what packages are attached by the user, the packages require kind of an internal environment called the namespace, and that is where the function is defined. So the namespace is going to be kind of the enclosing environment of the function, right? And so every function in a package is associated with a pair of environments. The package environment, which is where the name exists, and the namespace environment, which is kind of its enclosing environment where it's defined. Okay, so the package environment is the external interface to the package. This is the environment where the R user, which the R user uses to find a function attached in a package, okay? And its parent is determined by the search path, right? So the package environment is where kind of the names exist. That's going to be like the binding environment, and that's where the search path finds it, okay? And you can use the double colon operator to kind of access a function directly from the package, okay, regardless of the search path. And so, you know, for example, if you load up the library Mosaic, there's a mean function, and there's a mean function that exists in base, okay? And so, you know, something like, so when we're searching for names, the names exist inside the package environment, okay? But the function exists inside its namespace. This would be the enclosing environment, okay? And that's the internal interface to the package. So therefore, when you call standard deviation, it's going to find the name through the search path and find the binding environment, this package environment, okay? But the standard deviation function itself is defined. Its enclosing environment is namespace stats. And this will always kind of point to the correct parent, so that when, regardless of kind of the search path, and so it will always, when it calls for the variance function, it's always going to find the correct version of the variance function. And it doesn't matter if there were other libraries loaded before it or after it or things like that, okay? And so when you call for standard deviation and it looks for the variance function, it's going to use the namespace environment, and that's how it's going to find its variables, or the, you know, function names like variance. Is that all right? It's a little confusing, okay? But as far as, you know, this namespace goes, okay, and it's searching for this variance, we don't want it affected by kind of the search path, okay? And so the environment where the function is defined and how it's going to search for its things that are not defined inside the function, is going to be done via the enclosing environment, okay? And that's through this namespace. again, you probably don't have to worry about that unless you start writing your own R packages, okay? And some of you probably will start writing packages at some point in your career, but a lot of you will not, and so you don't have to worry about it. Okay, every time a function is called, oh, you know what? Let me give you another quiz answer. Second quiz answer for today is A. A is an apple. A as an apple is the second quiz answer. A, okay? Every time a function is called, we create an execution environment. The execution environment is the environment where the values inside the function are held and they disappear as soon as the function is completed. All right, so here I've got this function. H takes x. Inside x, we bind the value 2 to a. We return x plus a. And we're going to execute h of 1 and take that value and associate it with y. Okay, and so this is what the picture looks like. Okay, so first we call the actual action happens here when we call h with 1. Okay, and so x takes on the value 1. Okay, and so here we create an execution environment where x takes on the value 1. X gets 1 inside the execution environment of h. Inside that environment, a gets the value 2. A is bound to the value 2. And so we have x gets 1 and a gets 2. And then we can return x plus a. We're going to do 1 plus 2, and we're going to return 3. Okay. As soon as we return the value 3, this execution environment disappears. The execution environment goes away as soon as we return the value 3. And that value 3 is bound to the name y. So y gets the value 3. All right, and that's an execution environment. So the important thing is just that it exists while the function is running. As soon as the function is done, it disappears. So when you call a function, it creates an execution environment. The execution environment technically has two parent environments: the enclosing environment where the function is created, and the calling environment where the function is called. If you created a function in the global environment and called a function in the global environment, then the calling and the execution, enclosing environment and the calling environment are going to be the same, okay? Because it was created in the global environment, so that's the enclosing environment. If you call it from the global environment, that's going to be the calling environment. And so the enclosing and the calling environment are the same. But in some cases, you might call a function from inside another function, right? And in that case, the environments are different. So R's scoping rules, normal scoping rules, is that it uses the enclosing environment. So if the function is looking for values, it's going to look for values using the enclosing environment, okay? R also supports something called dynamic scoping, where you can search for values in the calling environment, okay? And that's done via the function get, and I've got an example of that as well. All right, so here's our first example. X gets the value 0 and y gets the value 10 in the global environment. And I define f inside the global environment. Inside f, x gets 2 and y gets 100. And I define h inside of f. So the enclosing environment of h is f, okay? Inside of h, x gets the value 50, and it's going to return x plus y. And we call h from inside of f, and so f is the calling environment of h as well. All right, so when I execute f, what is it going to return? Okay, so when I execute f, it's going to return the value of h. And when it returns the value of h, it's going to say, okay, x gets 50, and we need to return x plus y. So it's going to do 50 plus y. H is defined inside of f. So it's going to search the enclosing environment, and it's going to say y gets the value 100, and this thing will return 150. Is that all right? And so it returns 150, okay? Because h was defined inside of f, so when it's searching for y, it's going to look inside the environment for f, and it's going to take the value 100 here. Returns 150. Okay, here's another example. X is 0 and y is 10 in the global environment. Inside G, we have x gets the value 2, y gets the value 100. and it calls H. H now is defined, H is defined inside the global environment, okay? And inside H, X gets the value 3, and it's going to return the value X plus Y. All right, so if I execute H here, what is it going to return? Thirteen. Yeah, okay. It's going to take X is 3, and it's going to search for Y. H is defined in the global environment, and it's going to take Y as 10. It's going to return 13. What about G? What is G going to return? Okay, when we execute G, X takes 2, Y is 100, and it executes H here. Okay, and so when it calls H, inside H, we get X is 3, and it searches for Y. It doesn't find Y inside of H, so where's it going to search? It's going to search the global environment because H is defined inside the global environment. Its enclosing environment is the global its enclosing environment is the global environment, and so Y is going to take on the value 10, and it's also going to return 13. So this will return 13, and this will return 13. Okay, so H returns 13, G returns 13. Is that okay? Because H is defined in the global environment. Over here, H was defined inside of F, so it takes on the value here. Here, H is defined in the global environment, so it takes on the value 10. Even if I call H from inside of G, it still takes the value 10 from the global environment. This is an example of dynamic scoping, okay? Here, it's inside of H, okay? It's going to, X gets the value 3, but Y gets the value from here, parent frame. It's going to get the value from the calling environment, okay? So when I call H, it's going to say, well, where did you call this function from, okay? So when I call H from the global environment, okay, it's going to say X is 3, and it says, oh, you called H from the global environment, so we're going to search the global environment for Y, and it's going to get 10. And this is going to return 13. If I call G, all right, inside G, X gets 2 and Y gets 100, and we call H, okay? Well, inside H, X gets 3, and then it says, well, what is the value of Y from the calling environment, okay? Well, because H was called inside of G, it's going to take the value 100 from the calling environment, okay? And so now X is going to return 3 plus 100, and G is going to return 103. So H returns 13, G returns 103. All right. Is that okay? The difference between this and here where we use dynamic scoping by using the get function. Okay. The last bit, this is on super assignment. Let me just go ahead and give you your last quiz answer. Last quiz answer for today is the letter C, C as in cat. C as in cat is your last quiz answer. C as in cat. Okay, so super assignment. The summary of super assignment is don't use super assignment, okay? I can just say that and then we can be done with the section, okay? But I want to show you a few examples of how it works. But overall, the recommendation is don't use super assignment. You might see other people's code and they might use super assignment, but super assignment just leads to situations where it can be confusing and things like that. But anyway, let's just talk about it, right? So the regular assignment operator creates variables in the current environment, and that's how we're used to doing things, okay? The super assignment operator doesn't create variables in the current environment, but modifies an existing variable that's found in the parent environment, okay? And if the super assignment does not find an existing variable in the parent environment, it climbs the scoping ladder until it finds the variable it's looking for. And if it reaches the global environment without finding the variable, it's going to create the variable in the global environment. Okay, super assignment should generally be avoided. And this could just be the summary of this entire section here. All right, but let's just try a couple examples. I get X, Y, Z in the global environment. Those are all the value 1. F inside F we're going to super assign the value 3 to y. Okay, and so right now, if I ask for y is just the value 1. But if I execute f, then this operation takes place, and y takes on the value, y is going to get the value 3. Okay, so f gets executed, we super assign y to 3, or 3 to y, and we return y. So f returns 3, and we can see that the y in the global environment has now changed to 3. Okay. Here we have x, y, z. We reset them to be 1 in the global environment. I have f. Inside f, we're going to assign 2 to y, super assign 2 to y. Inside of f, I define a function g. And inside g, I super assign 3 to z. And we're going to return the value x plus y plus z. Okay. So what happens when I execute f, we assign 2 to y, and this is going to change in the global environment to 2. And then it says return g, so we execute g, and it's going to look for 3, or z, and it's going to modify z to be 3. Now it first searches the environment for f, and it doesn't find a z, and so it goes a higher level, and it finds z here, and it's going to modify this to 3. And then it says return x, and again, it searches for x here. It doesn't find x here. Searches for x here, doesn't find it, and it finds x here is 1. Searches for y. It doesn't find y in here. It doesn't find y in here because this modified this one, and so it's going to find y is 2 here. And it searches for z. Z doesn't exist in here. Z doesn't exist in here. Z exists in here with the value 3. So it's going to return 1 plus 2 plus 3. It's going to return 6. After running f, what are the values of x, y, z in the global environment? It's going to be 1, 2, and 3. Is that okay? It can get a little bit wonky and a little bit tricky. All right. So here I got x, y, and z, again, 1 in the global environment. They're all 1s in the global environment. Inside of f, I locally assign 2 to y. Locally assign y, or 2 to the value y. And then I do super assignment 4 to y. And this one does not touch this. It immediately goes to the higher scope, and it's going to change this to 4. Okay, so this has the value 4, and there's a 2 in here. And here I'm going to look for z. There's no z here, and we're going to change this z to 3. So when we return x, y, and z, we look for x, no x here, no x here. We find this x is 1. We search for y, no y here. There is a y here. Y is the value 2 inside of f, so we're going to take 2. We search for z. There's no z here, no z here. Z has been modified to the value 3. So it's going to return 1 plus this 2 plus 3, and we get 6. What are the values of x, y, and z in the global environment? It's going to be 1. This is a 4 because of this thing, and this is a 3. So we're going to get 6, but we're going to get 1, 4, and 3. Okay, because y is 2 in the scope of f. All right, here, x, y, z, again, 1 in the global environment. Y gets 2, z gets 10 locally. Okay, we modify 4, y to be 4 in the global environment. So this will become 4. Z super assign 3 to z. It's going to come up here, and it finds the z here, and this is going to get the value 3. Okay, and it's not going to touch this one. It finds the z here, and it's satisfied. It's not going to go to the global environment. Okay, so this one will get changed to 3. It asks for x, y, and z. Searches for x, no x here, no x here. It takes x as 1. Searches for y, no y here, and it finds this y. This y is 2. Okay, searches for z. There's no z here. It finds this z. What is the value of this z? It's been modified to 3. Okay, so this z takes on the value 3. So it's going to return 6 again. 1 plus 2 plus 3. what are the values up here? This is still 1. This has been modified to 4. This one remains unchanged and remains 1 because this thing, the superassignment 3, modified this one. Okay, so F is 6, 1 plus 2 plus 3. The values in the global environment are 1, 4, and 1. Is that okay? All right. Okay, there's, I'll let you do this, but basically all of this stuff just says avoid superassignment, don't use superassignment. And we'll just call it a day here. I'll let you read these slides on your own. Monday is Martin Luther King Day. Okay, so there is no lecture. You know, on Martin Luther King Day, we kind of, you know, we reflect on our nation's, you know, I don't know, just difficult history of racial disparity. We do want to celebrate the change in achievements brought about by Dr. King and, you know, other civil rights leaders, but also we still acknowledge the work that still needs to be done. So that is Monday. That is a holiday. There's no lecture, and so I will see you guys on Wednesday. Have a good weekend, and we'll see you guys on Wednesday.